Hello, participants. Thanks for taking the time out of your busy schedule to join us here today. For me personally, it's a pleasure and a privilege to be able to present new ideas, new technology to you. We're talking about optimizing transmission right of way and environmental protections. I'm going to give you a little bit about HVCC, High Voltage Covered Conductor, what the system objectives are. We'll talk a little bit about the 69 kV spacing cable system and tree wire system. We'll talk a little bit about the 115 kV system. Then we'll get right into what is supposed to be the main gist of this presentation, our right-of-way concerns. How do we expand capacity in existing right-of-way? How do we, one inch from each other? That's how good the insulation is. So the poly is going to provide a high impulse strength. It's going to provide a high BIL, 60 hertz withstand, and it's going to withstand short-term either phase-to-phase contact, phase-to-ground contact, phase-to-animal contact without faulting. So we want to make it much more resilient to the environment in which it's installed. The design objectives for that covered conductor is what we want to do is we want to limit the charging current or limit the surface current that's available on the outside of that jacket. We want to keep those phase conductors separate. But if they do touch, even for momentary or extended momentary, we're not going to have damage and we're not going to have an outage. And we say that control of surface charging current is key to virtually everything. We want to prevent tracking. We want to minimize safety issues in case anybody does touch it. And we want to make sure that we've got that current floating around the outside of that jacket 40, 50, 60, 70 years. It's not going to degrade the quality of that insulation. We're not going to feed it. So we want to maintain that insulation integrity over the entire useful life of that system. The conductor insulation system has 3 layers. The first layer is a conductor shield. That's basically going to smooth out the electric fields when we're in contact with a ground object. It's going to minimize the partial discharge. Going to give us a higher BIL, and it's going to give us a longer useful service life. The inner dielectric, you can see it's white there. It's really see-through. It's translucent. It's a very high BIL, high 60 hertz withstand, low density molecular weight polyethylene. The other thing that gives us is we use a really soft, low density so that we can facilitate stripping for taps and junctions and transitions. The third layer is what we call the outer jacket. That's where all the tricks are. It's a high-density polyethylene. We source the highest density, high-density polyethylene we can because we want abrasion resistance. There is the anticipation that conductor someday is going to touch a tree or rub on a tree or tree branch. We don't want to have abrasion, so we want very high abrasion resistance. That outer jacket, high-density polyethylene, is also where we put the track-resistant adder. We don't want to have tracking. It's also where we put the UV inhibitor. And that UV inhibitor is a chemical UV inhibitor. It's not fugitive. It will not leak. It puts a chemical umbrella over the molecular chains and protects them from UV rays. And lastly, it's where we put the color. We have black, we have gray. And of course, by Ohm's law, if we have higher voltages and we want to keep the current down to 1/3 or maybe 1 milliamp for the higher voltages, we're going to have more insulation. So you can see at 15 kV, the 2 layers, the A is the semicon, the B and the C are the N and the hour laters. You can see at 15 kV, we have 75 plus 75 mils, 150 mils, which is about 3.6 millimeters. Meanwhile, when we get to 69 and 115, we've got 250 plus 250. We have 500 mils, which is essentially a half inch, or about 12.5 millimeters. So that is the insulation thickness. So that's the theory. That's the conductor. Let's talk a little bit about high voltage covered conductor impetus and history. In the 40s and the 50s, New Englanders were kind of tired of outages from storms and trees. They just got fed up. Bill Hendricks invented spacing cable, came in 1950. It was first adopted in the state of Mass, then New Hampshire, then all of New England, the whole U.S., then slowly Europe, Japan, Scandinavia, Asia, the whole world. In the late 80s, Electric Power Research Institute asked Hendrix to move from 46, we were only at 46, up to 69 kV. So we had a joint R&D project with Florida Power and Light. We used their labs down in Juneau. And 69 kV spacer cable was developed and introduced in 95 and commercialized. We now have 69 kV all over the place. In 2007, Hendrix was asked by BPA to develop 115 kV high voltage current conductor. So we submitted a joint funding statement to the Department of Energy jointly with the BPA, but we were luckily turned down, and we decided to go it alone. From 17 to 2024, I'm getting a little bit ahead of myself here, but system design was complete, patents acquired, pilot was installed at Versant, formerly Emera in Maine, in 2019 with PD monitoring every 3 months. We just recently finished Liberty Utilities there, rail 2.5 mile 115 kV spacer cable circuit. And in 2024, more good stuff coming.